Okay, we're learning about entropy. So the entropy of a simple matter increases as it changes state from solid to liquid to gas. And so we can think of what's happening with these particles, and they're becoming more disordered, right? Here, they're all in nice rows, all lined up, and they stay that way. Here, they're just jumbled around. Here, they're spread apart, okay? So that's the more normal way of thinking about things. The more scientific way is to say, well, there's more energetically equivalent ways of arranging the particles in the gas state than in the liquid or the solid state. What the heck does that mean? A gas has more ways to distribute its energy. So the gas molecule can rotate, it can translate, and it can vibrate, I think. As a solid, the only option is vibrating. The particles can't move relative to each other. They can't turn around. So each of these different types of motion is a different way to distribute the energy to be in a different state and yet have the same energy. So like these guys back here, right? There's all these different ways that the particles could be distributed. So any questions about that? So the entropy is going to increase when you go from a solid to a liquid to a gas, liquid to a gas. So we should be able to remember that. And another thing that will always be an increase in entropy is when you increase the number of moles of a gas during a chemical reaction. Because that means that you started with something that wasn't gas or fewer molecules, and now you've got more molecules of gas, and so that's a lot like these two here, right? Something's becoming a gas. In any of those situations, we would predict that the change in entropy was positive, more disordered. Okay. Predict the change in entropy for each process. Water boils. Positive. Are you positive? Yeah, water boils. It's going from a liquid to a gas. That's a positive change in entropy. It's becoming more disordered, right? Particles scattered all over the place now. How about iodine gas going to iodine solid? That's going to be negative because you're taking these random molecules that are far apart and just doing their own thing, and you're cramming them all into a crystal. And they have to sit in lines and rows and just be still. So that's negative, that entropy going down. And then this one. It's going to be positive. Why? Because we have more moles of gas on this side. That side had no moles of gas. It was all solid. Over here we have solid also, but now we have moles of gas, and the gas has more entropy, and so we have a positive increase in entropy. Any questions? There's some things in this chapter that, we're going to talk about in some detail, but really all that needs to come out of that is you need to have a general understanding of how it works. We have to talk about some of the details in order to understand it. So this is one of those things that you should be able to do, say, on an exam. Okay, so we can calculate the entropy change. A change in state is always accompanied by an exchange of heat between the system and the surrounding, right? How do you make an ice cube melt? You put heat into it, right? So entropy is related to the distribution of energy among the particles. So we can say that the change in entropy when a system exchanges a quantity of heat, Q, with its surroundings at constant temperature is delta S. So delta S is Q over T. And we put ReV here indicating that this has to be a reversible process. So this is the same kind of Q we saw in Q equals MC delta T, right? MCAT. So entropy is actually a measure of energy dispersal per unit of temperature. And so now we understand why the units are joules per Kelvin. See over here, if we express this in joules and this in Kelvin, the units are going to be joules per Kelvin. And that's the unit, the basic unit for entropy. So substance melts, it's absorbing energy from the surroundings. So Q is positive coming into the system, right? That energy becomes dispersed into the system. The entropy of the system increases because there's more heat in it now. Okay? Now, what's a reversible process? It's a little bit like a unicorn. There's not very many of them. It's a process where if you make a teeny, teeny, tiny change in something, it'll go the other way. So an example is ice melting at 0 degrees Celsius. You've got some ice, and it's in a container. It's 0 degrees, the whole thing in there. And ice will melt or freeze at 0 degrees, right? So if we took a little tiny bit of heat out of that 0 degrees Celsius box, we'd lower the temperature a little bit below zero, and any ice that's in there is not going to melt anymore, right? And any water that's in there is going to freeze. So the ice was melting, now we make a little teeny tiny change, and it's freezing again. That's a reversible process. This doesn't happen on the countertop. So you put an ice cube on the bench up here, and normally it's been like 72 in here, and the ice will melt, right? Because that's above the melting point. Well, if we drop the temperature 4 degrees to 68, which is like what it is right now, does that cause it to stop melting? No. You'd have to change the temperature a lot before you could get it to stop melting. You'd have to get down to 0, actually. So reversible processes are in equilibrium. They are highly idealized, meaning we don't actually see them very often at all. But scientists will often use something like this to make the thought process simpler, because we can think about, well, what's happening if we take all those other complicating factors out? What's happening here? And then when we understand that, we can figure out how it applies to actual things. So calculate the change in entropy that occurs in the system when 100 grams of acetone vaporizes from a liquid to a gas at its normal boiling point. Well, the equation we just learned is what we're going to need. The change in entropy is equal to Q reversible divided by the temperature in kelvins. Okay? Well, the temperature is easy, right? We got this. We can change that into Kelvin. No, I'm not going to do it in my head. I now have COVID brain on top of chemo brain. Yeah, great. $329.25. Okay, so that's the temperature. Q. What's Q? Well, they didn't give us Q. They gave us the heat of vaporization. Remember what that is? This is the amount of heat needed to vaporize 1 mole of that thing at its boiling point. So it's this many kilojoules for each mole. What we need here is a unit just of energy, like joules. What we really want there is joules. So how could we turn this delta H into joules? We could multiply by moles. the unit we want to get rid of here is moles. Well, they didn't tell us how many moles there are, but they gave us a mass, and they gave us a formula, right? So we had 10 grams of acetone. We can convert that to moles, and then we can multiply by delta H. And then entropy is usually given in joules per Kelvin, and this is no exception. So let's just go ahead and convert this to joules. So this conversion here, what's different, the denominator has K, kilo. Kilo means 1,000. So the 1,000 is on one side of the line and the K is on the other side of the line. This is what we were given up here, 29.1. And kilojoules is on top, so the number is on top. And then here we need the molar mass of acetone, 3 times 12.01 plus 6 times 1.008 plus 16, 58.078. So that's the mass of 1 mole. So here the number's going to go in the denominator. So when you use dimensional analysis and you get all the units in there and you get the units to work out, then you don't have to remember, am I supposed to multiply by the molar mass or divide? You just put it in with the correct units. So what do we get here? 10 divided by that times 29.1 times 1,000. So 5010.5 joules. And that should have 3 sig figs. So that's Q. So that's what goes up here. So then we take Q and we divide it by the temperature. And we get 15.2 joules per Kelvin. Any questions? The reason that they use joules per Kelvin is because the numbers we're going to see for entropy or changes in entropy are pretty small. And so joule is a good unit. When we're dealing with heat, Q, and delta H and stuff, it's much more. And so that's why we almost always use kilojoules. Any questions?